In this video, I'm going to be covering measurement of angles using a variety of tools, as you see here. Some of the tools that we'll be covering include the Bevel Protractor, which is going to be one of your main hand tools. We'll also talk about a digital protractor as well. We have an angle gauge set, which helps you compare angles visually. And we have a machinist square. And of course, we can actually measure a few angles using a caliper, not necessarily measuring the angle itself, but verifying the symmetry of angles in a lot of relationships on prints and on parts. So we'll talk about that. Those will be our hand tools that we're going to cover. And for surface plate tools, we have a sine bar and a sine plate. I'll be demonstrating how to use a sine bar. Sine plate is just a wider version of a sine bar and can actually combine angles. And you'll need a height gauge for that. So if you're using a sine bar or a sine plate, you're going to need to use a height gauge and a test indicator. So if you haven't watched the videos on those, you may want to check those out when we get to the sine bar. And then last gauge we'll be talking about is angle blocks, which also work with our surface plate. So let's get started. Well, first of all, let's talk about the purpose of angles. When you're inspecting, looking at these prints, you're going to want to consider, what is the purpose? What is the purpose of the angles that you see on prints? One of the main purposes is a mating surface. So when you have maybe two parts that are going to be rubbing on each other on a certain angle, or even stationary mating and assembling, oftentimes, those surfaces complement each other, and they many times those angles will be held to a tighter restriction, to a smoother surface, because there may be motion involved. The next one might be a clearance surface. So for this part, it may just be, you needed the angle block needed a clearance just to clear another part for assembly or for operation. And those angles tend to be more open tolerance, less surface finish requirements. And that's just because, you design it so that you can just cut away a clearance chunk and it's not a precision feature. The last one would be a positional feature, and that tends to be for hole patterns. So we'll take a look at this smaller part here. This smaller part has 4 holes for assembling this flange onto some sort of face. And sometimes they'll be called out as an angle. Sometimes it'll be called out as an equal spacing. We have to look at our print to decide. We have a print that we're going to go over that has some different styles of dimensioning for measuring these angles here. So we'll talk about that when we get to that as well. But it's usually for positioning holes or other features for assembly. And oftentimes you have the option when you're working with a part, you could use angles to dimension it. You could use XY coordinates. There's no real requirement, so you have to look at your print to see what they chose. Those are the 3 main, when you're looking at your prints, if you see tight tolerance, you see angularity requirements, those might be assembly features. And if you see open tolerance, those are probably clearance features. So we're going to get started with our first tool. We're going to talk about the universal bevel protractor. So this is a pretty cool tool. I really like using these. You have a clamp in the middle that will allow you to rotate these 2 faces into any angle that you want to measure, from this surface to this surface. And in fact, you can use even more surfaces on these blades that you like. These blades unclamp and slide, so we can move them in and out to get the angle we need. We can even take this out, and let's see if I can demonstrate it. Take this out. We could flip it around and put it back in if we needed to. We can also grab different blades and assemble them with a longer blade. It's a little bit tricky to get the blade in. Check out the secondary camera here. You can see right in here, there's an alignment tab. There we go. You can kind of see that now. As I rotate this knob, I can get this this blade in. So it's not always easy, especially with this particular protractor. Let me struggle with this for a second. There we go. So you gotta kind of wiggle it in. Once you're in the track, you can clamp it down. So when you're clamped down, with this knob here, the track won't slide. You can unclamp it, move the track, clamp it down again, and take your measurements. So this 12-inch blade is a little bit overkill for what we're going to be doing. So I'm going to switch back to the 6-inch, or 5-inch, I believe. Slide you in. And what's nice about the bevel protractors, you have this clamp here that will help you move the blade. You have a knob here you can loosen and tighten down when you get to the angle you want, so that you can take a quick reading, a nice accurate reading. So you can take your measurement away, clamp down, and then look at your reading. We have a scale here that's very fine, and it's reading in 1 degree increments. So you can get really nice, visually you can really see if you're lined up on a degree, or if you're in between two lines. You're just going to have to estimate how far in between each degree you are, but that's fairly easy considering how magnified this glass lets you zoom in on it. Some other style of protractors will have a fine adjustment knob here, which will let you manipulate the protractor by actually moving this thing. This feature doesn't have it, but as you see on the picture here on the right side, there's a fine adjustment knob which may or may not which would help you finely rotate this just by twisting the knob, so you don't have to do it by hand. But it's a great tool. I use it all the time because you can get different angles at different rotations. You can use this surface, you can use this surface, you can use pretty much any surface that you see here highlighted. They should be all ground precision angles. So, depending on the quality of the gauge you bought, it should be ground and precise, parallel. And so you can use these edges on the part. You can use these edges on the part anywhere that the edges reach. So I'll demonstrate a couple of measurements real quick. So for the 40-degree angle, I'm just gonna kind of tightly rest that on there, bring it up to the camera, and let's see what it was machined at. It's under just a hair over 40 degrees, maybe 40.2. Not a huge difference. We can also check it from the other side, and we'll register it on these, and we're reading, let's see, I'm not getting a good registration. There we go, right about 50 degrees. So if you take a look at our print here, the PM02 angle block, we see we have a 40-degree angle from the bottom surface to this angle. Now, if you don't have this print, please check out the website. Pragmatic Metrology website will have this print available for you to download, print, and follow along. Should have mentioned that earlier, but We have a 40-degree angle there, so it was machined at the right angle according to the protractor. If I wanted to try and get, a direct measurement between these two angles, let's see if I can, it may not be possible, but let's see if I can use the surface plate. Might be running into a clearance issue with the surface plate. Yeah, I'm not going to be able to do it. But you can get creative. You probably have to raise up to get some clearance, but there's another way you could do it. I've done many angles in this configuration where you're measuring this is not the most direct way to measure this part, but this would be another way you could do it, is you could set it up on the surface plate and get it this way if you have the surface plate on the bottom. So you have a lot of ways you can orient this blade and rotate it around. There's a 360-degree scale, so as you're using it, you may need to do some compound math with 90-degree angles or 180-degree angles. Certainly, it may not always be direct, so be careful about that, especially when you get around 45 degrees. The compound math gets a little tricky because you're not quite sure if you're reading 48 degrees on the bevel protractor. Should you be doing 90 minus 48? Sometimes it's not always clear. It's not always direct, and I've seen a number of people make that mistake. They read it directly when they should be using a compound angle because of the two surfaces that they chose may not have been the exact same surfaces that the print chose, and they may have chosen the compound angle not realizing it. So be careful about that. Do some sanity checks because you don't want to make that mistake and pass a part or reject a part that doesn't need to be. All right, we talked about this as I demonstrated. When we're talking about calibration, so let's clear our surface plate a little bit. And to calibrate it, you take a calibrated surface. Well, I would say to check calibration. To check calibration, take a calibrated surface plate, and you're going to rest your protractor, unclamp it, let it seat down. Kind of give it a little bit of a push, not too hard. And it's a little bit tricky for me to do demonstrating it, but when you check this, and clamp your blade. I didn't have my blade clamped. When you do this, put it down, rest 0, clamp it down. What do we have? We have, I call that 0. It might be a tiny bit off because I'm demonstrating it backwards, or I may have a piece of dust, but for the most part, I'd say it's in good calibration right now. So that's a good way to check it. If you have another angle block, besides a surface plate, add another angle, you can check it. You could bring in, this looks like a 45-degree block. I wouldn't recommend bringing in a loose piece like this, but actually if you had a solid piece that you have 2 angles on that you can measure, that's at a known angle, it's calibrated, you can do that. It's a little bit trickier with one piece because then it's hard to stabilize both, but that would be the, if you had another block manufactured at a certain angle, you could check it that way as well as a mid-range check and also a 0 check. So that second bullet point, in the surface plate lecture, we talked about parallax error in indicators. Well, with certain protractors, not this one, but certain protractors, you can get parallax error. This one's got a measurement reading pretty much on the same plane But sometimes these readings and the zero mark, as you rotate around, are at different planes. Sometimes they overlap. Different styles, might have a needle that points out and rocks around. So if you're at an obscure angle, sometimes you can make the wrong reading versus being dead on straight ahead. So that's what parallax error is when you're kind of looking at a sideways angle and that needle, instead of being dead on each other, from your perspective, it looks like the needle is casting a shadow on another number instead of the right number. So check out that surface plate video for a more thorough explanation, but you want to watch out for that. You want to be reading dead on with the bevel protractor. And of course, make sure your edges are registered securely. If you don't have a good, nice, firm grip and holding it steady, it's rocking, it's not going to give you any good data. So, really hold on to it. Get a good, nice, firm grip. It's not too delicate of a gauge. You can't really crush it by squeezing too hard, but just hold it firmly, and treat it gently. Set it down nicely. Now, there's a nice feature about bevel protractors and height gauges. It's that you can assemble them together. And there's a clamp that has a wider mouth on the bottom here to accommodate the thickness of this bar. Now, unfortunately, I do not have a compatible clamp and a compatible bar. As you can see, it doesn't want to fit in, but that's just because I have I have probably 3 different manufacturers involved. I have a height gauge, a clamp, and a bevel protractor from different manufacturers. So unfortunately, these don't go together. I can't demonstrate that, but we can still talk about it. It's still a pretty cool feature that I like to use for larger parts. So if you can clamp it on, you can use that. You can use the height gauge to raise and lower the bevel protractor, so it's not bulky, and you can get a direct reading from the bottom surface to whatever angle you have. So if your print is calling out the angle between these surfaces, you can get a direct reading this way. It's fairly easy. You just raise and lower the height gauge. And as you do that, you can unclamp this, and I'll demonstrate. If I'll pretend my arm is raising and lowering the height gauge. Let me raise this up. As you lower it down, this bar is basically you can kind of force it in, and it'll slide up and down, but it'll actually register quite nicely as you're moving up and down. So you may have to slide the part into it. What I sometimes do is I'll lower the bar, and then I'll slide the part in, and then it'll self-register, holding the gauge in the vertical position the same, and then slide the part in until the bevel protractor lines up. So it's a cool way to get a direct reading. Now it's going to be highly dependent on your accuracy of your height gauge. So if your height gauge is not in a good perpendicular condition, if there's some perpendicular error with your height gauge, then it's going to introduce that error as you move further and further up. But most people are keeping their height gauge in good condition, and it's more than adequate for what we're working with when we're measuring an angle. So this little attachment, not too much money, might run you $20 maybe, or even less than that. You want to, like I said, make sure you've got the same manufacturer as much as you can. Otherwise, it's not a bad idea to try and modify this, or modify a height gauge bar, modify a protractor if you're going to dedicate a protractor to a height gauge situation. But it's going to be important to make sure you've got a nice registration on your height gauge relative to the clamping bar. Actually, I don't know what this piece is called exactly, but you want to make sure that your height gauge, when you are registers parallel to the bar, because this bar is designed to be parallel to the clamp here. So just keep those tips in mind. If you're thinking about doing it, I recommend it if you're working with some larger parts. I've done it many times as I've worked with large parts, and it's been a big help. We're going to bring this back for the sine bar, but I'll move it out of the way for now. Okay. Now we're going to move on to the digital protractor. So as opposed to the bevel protractor, a digital protractor does not have any moving parts. The protractor itself is what moves around. So I don't have one of these available, but I think it's a nice topic to talk about if you're working with large parts. Again, maybe weldments, large frames, just even just big pieces. If you're machining, you've got the part in the machine and you can't get a bevel protractor on it. What you can do is, if you pretend this is a digital protractor, is you can zero this on any surface with the 0 button, and then move it to another part. It could be the parts, could be the angle you want to measure and zero off of. You can zero off this and you want to measure off this, and they're on different planes. That can be a good way to do it. Just zero, and as you rotate this around, it's giving you a reading from your 0. It's fairly accurate. I would say it's not quite as accurate as getting a direct solid reading, but it's a great way to verify quickly that you are, you're not at the wrong angle for your machining or your welding. And oftentimes these things, some of these gauges will work off of multiple surfaces. Some of these gauges will only work off of a few. So do a little research on the one you think you might want to purchase. These can range from like $70 up to like $200 depending on the manufacturer. But again, if you're working with larger parts a lot, you're working on a situation where you want to very quickly measure an angle that's at different planes, and you can't get an angle at these different planes without a CMM. You want to do it on the production floor. This can be a great tool for checking it. So I like them. Unfortunately, I don't have one for this video, but check them out on, look them up online, do a little research. And this one from Proline, there's many options out there. So we're gonna move on to the angle gauge set. So next up, we talk about this this range of angle gauges, and these are like a comparison tool. So you can machine something or fabricate something, whatever, and you can use these gauges have many different angles on them that are at, let's see, this is a 55-degree gauge. It's got the 55 degrees, it's got compound angles with 55 degrees, and so you can quickly verify, your profile is correct. Now these should be probably, calibrated, and they should pass calibration every time because they're not going to see a lot of wear. But typically you're not going to use this as your final checking gauge because it's hard to say that it's going to be in tolerance just based on this, depending on your print. Maybe some clearance, if you look at your print and it's a bunch of clearance angles, and they should have big tolerances, which may allow you to use these. Otherwise, it's kind of just a quick sanity check, verify that on the machine or in the production process, everything's moving smoothly and at the right angle. And you're going to use a bevel protractor or another tool to verify it's actually within tolerance. So go ahead and, you could calibrate this in-house if you've got an optical comparator and you write a procedure to do that. you could send them out to a calibration lab as well, and they're probably going to use an optical comparator or something like that. Now, the way you're going to use it, you basically, you're going to take apart and you're just going to start grabbing, it's a 40-degree angle as we've talked about. I'll grab the 40-degree bar, and sometimes, you're going to have to grab a 1, 2, 3 block, but if I look at that, that looks like 40 degrees to me. Go ahead and check out this camera feed as well. It looks a little better looks a little clearer, but otherwise I've got a 40 degree there. I can flip this around and we can try to line up this angle. Looks like that's 40 degrees based off of this angle. And if I try to do this one, oh yeah, see, it's definitely not 40 degrees because we have a compound angle off of these two faces. So I'll grab, should be 50 degrees. I'll grab the 50, and the 50 should line up pretty perfectly. So that's basically when I use it. Sometimes you don't need to use a 1, 2, 3 block. Depending on your angle, you can get a direct reading with some of these, whether it's an internal angle or an external angle, whether it's acute or obtuse, will determine whether you need to bring in a 1, 2, 3 block or not. But these are a great way to get a quick check. So put those down. So here I have pictured a few methods. You can also use these to verify chamfer angles. Verifying a chamfer angle is typically done by verifying the chamfer tool. And you'll take that tool to an optical comparator. Maybe you'll use something like this to verify the chamfer angle as well. But if you want to do it on the part, what you can do is you can grab the base of it, the whatever angle, this is a 90 degree because I know it was a 90 degree chamfer, and you can drop that in, and you're just going to have to kind of look at it and see, did you, how closely can you visually verify that you got a 90 degree chamfer. And typically, it's gonna be a lot easier to do the chamfer tool than to do this, right? But if you're not, if you're in the inspection department, you don't have the tool available, you don't know what tool is used, this is how you're gonna have to do it. It's not a bad way to do it, but it's not an easy way either. Now for actually measuring the depth of the chamfer, we use something called a chamfer gauge, which will measure how deep the chamfer was. But these will tell you that the angle of the chamfer, because sometimes the angle of the chamfer is controlled for clearance purposes with the bolt or another piece that's going in. So next up, we're kind of blasting through these because all these tools only do really one thing. Next up, we're going to talk about the machinist square. So this precision square will basically tell you, are you 90 degrees or not? Sorry about that. Did you machine this at 90 degrees? If you can see a problem just by holding up a square to the light, then this is a visual indicator. I can see some light when I register on this face and I look at this face. I can see some light between the part and the blade. So there's probably a little bit of 90 degree error between these two surfaces. But it's great for setting up parts. It's great for just quick checks again. You can get these calibrated and use these as a passing check, but typically not recommended because it's not going to give you really any numbers. There are other tools that will give you a number. A height gauge will give you an indicator up and, run an indicator up and down a part, and you'll get a number of how far that indicator moves. CMM will tell you an angle. Bevel Protractor, of course, would tell you the direct angle between these. So this is kind of, again, It's a precision square, but it doesn't really have a lot of precision applications compared to a bevel protractor or CMM or anything else, because it has no readout. But I like keeping them around. They're handy for checking parts quickly, looking for quick errors. Let's see if we can see that error on the camera here. If I bring this in, I see a little bit of error between the top surface and the blade. It's not really showing up on the camera, but when I hold it up to the light, definitely can. And so, you can actually use the outside edges as well. They're all precision angles, so it has multiple uses. And there's some other styles. You see another style below that has some attachments you can clamp on. But that's more of a setup piece for machining or welding or fabrication. So stick to the bevel protractors, CMMs, height gauges as needed. They will give you an actual reading. This will just give you a quick check. So now we're going to move on to the sine bar. And the sine bar is a pretty cool tool. We use a sine bar to create an angle that complements our angle on the print. And so if this is a 40-degree angle and then we rotate the part 40 degrees, we make sure that the surface plate and the feature that we're trying to measure are parallel. So we kind of subtract the angle that way. And so that way we can verify with the surface plate, the angle was put in at the right, the feature was put in at the right angle. We're gonna need Joe blocks. So if you haven't watched the surface plate videos about Joe blocks, you may wanna check those out, but they're pretty precise tools. They're going to be what we use to form the angle. Here's my sine bar. And the sine bars have a little ledge here that will help you rest your part. There are bolts that you can disassemble the ledge if you don't need it or if it's getting in your way. I'm going to leave it on because it's actually going to help us for our measurement. So the first thing you want to do how do you decide when do you need a sine bar, when can you use a bevel protractor? You want to look at your print. And our print has on it, I've highlighted there, angularity tolerance of 5 thousandths relative to datum B. So besides a CMM, the only other way we're going to get this is with a sine bar. A sine bar is going to allow us to use an indicator and look for 5 thousandths of movement off of our indicator reading. And so we'll set that up to mimic the print. Datum B is the bottom. We're measuring this angle and we're looking for 5 thousandths of angularity. So when we set up our sine bar at 40 degrees, this is what it should look like. We should have the bottom, basically the top parallel to the surface plate, both at 40-degree angles. And so we're gonna run our indicator across it and verify our indicator doesn't read more than 5 thousandths. So the tricky thing for using a sine bar is the Joe blocks. How do you build a stack height to translate this to 40 degrees? So I already did this Joe block stack to save a little time, but this is now a 40-degree angle, and the way we figure that out is we draw. I'll even mimic the setup here with the television screen. So in order to figure out how high of a stack we need to form, we use the triangle formula. We want to figure out the length A here, this stack height. B length on the bottom there doesn't matter, but we're going to do length A relative to angle A. And it works out, the formula is equal to A times the hypotenuse, sorry, the stack height A, capital A, is equal to the hypotenuse, which is your sine bar, times the sine of the angle. So if we plug in the numbers that we were using, we have a 5-inch sine bar. And so that is our hypotenuse, our letter C. So we'll do 5 times the sine of the angle 40. And I want to quickly point out right here that if you actually measured how long this overall bar is, it's probably closer to 6 inches. But the 5 inches comes from the center of these pins that are bolted in. So it's center to center distance of the pins, and it's not the overall length of the sine bar. So that's an important feature. Most sine bars are going to be either 5 inches or I think there's 10 inches or 12 inches. But the most common one you're going to see is a 5-inch sine bar. It's a good size. If you're not sure, go ahead and quickly measure your center to center distance on your sine bar pins. But most of the ones you're going to find are 5 inches. So so we're going to use that for calculating our sine bar height. So if I do the formula 5 times the sine of 40, we can look up the sine of 40 in what's called a sine table here. And a sine table is just going to tell you the sine of the angle at every angle from 0 to 45 degrees or 1 to 45 degrees. So you can look at this table. You can also use a calculator. It's up to you. If you have an angle that's not in the table, you could have 40.5 degrees. Then of course you're going to have to use a calculator. But if it's in the table, you can go ahead and use it. So the table is telling us that the sine of 40 degrees over here, since we're trying to create a 40-degree stack height, the sine of 40 is 0.64279. So we multiply by 5 inches based on our formula here. We have the sine of 40 here, and we have 5 inches here. So we get a stack height of 3.21395. And in the surface plate videos, I've talked about how to stack Joe blocks together, how to choose the Joe blocks. So I've created a stack here that is 3.214. I've rounded a little bit because it ends on a 5, and I've rounded up, and it makes sense in this situation. But you could actually build this down to the 10,000th of an inch resolution if you wanted to, but because it ends in a 5, I'm going to round it up. I'm going to round up that 9 and call it 3.214. So let's do our measurement. So clear our table a little bit. So I have my stack height. I'm going to take my bar and just try to drop it on there without tipping over the stack height. Okay. Actually, before I do that, I'm going to get my indicator in position. Try not to hit the camera here. All right. So I've got my, so be careful not to tip over the stack height by applying force in this direction, or you'll tip it over. So try to just drop it. And as long as everything's clean and smooth, I've got a 40-degree angle on this surface. I'll take my part and we'll drop our part on very gently. Ooh, I almost did the thing I warned you not to do. So there we go. All right. Give everything a quick stabilization. And now, when I go to measure this angularity, 5/1000ths relative to B, datum B is what's rested on the sine bar over here. And we're gonna measure the error relative to this sine bar, because we've now kind of shifted the surface plate 0 up to an angle using the Joe blocks. So now if we take a look at our indicator, all right, I'm gonna shift everything just ever so gently, a little bit there, okay. All right, so if you take a look at our indicator, I'm gonna zero it on one corner. All right, looks like 0. I know it's a little hard to see on the screen. Take a look at this feed again. I'll remind you about that. And so now we're gonna drag it around and look for indicator movement. And I don't see a lot of indicator movement. I see about, oh, I'm falling off the part. Yeah, I see about half a thousandths in this edge here. It's probably a machining step over issue. But overall, I'm not seeing a whole lot of error. So we would say we're looking for maximum indicator movement of 5 thousandths, and I would say I have half a thousandth based on what I saw here. And so this part passes the angularity requirement of the print. So that's basically how you use a sine bar. You just set it up at your angle. We call it a subtraction angle, and then we should see 0 indicator movement when you run it over. All right, so when you're doing this one, you know, be careful. You can kind of accidentally tip the whole situation over by applying too much force with your indicator and whipping the height gauge around. So be careful about that. You don't want to knock everything over, especially if you accidentally set this up at the wrong angle. You get more of it. Your indicator will bottom out and maybe knock something over or damage your indicator. So go gently, be careful. If you don't need this this lip on the bottom, you could take it off and then your part would stop on the surface plate. So sometimes that's good for larger parts. This is a kind of a medium part, so we're okay with using it. But otherwise, you know, when you're done with your Joe block stack, just put them back in the box and you're ready to move on. So next up, we'll talk about angle blocks. So these work a little bit like the height gauge, or sorry, the sine bar, where you can set these up and rest your part against them. For the most part, they're great for setting up kind of fixtures for machining or fabrication. For final inspection, they don't have quite as much use. You certainly could, you know, use these as a visual indicator, you know, between the surface plate and the angle. That can be a use for them, but they don't come in a lot of angles. You know, they're not nearly as many angles as what you get with a Joe block set. So in some ways you're limited. I have a set here. So these kind of are just a visual tool. Again, kind of like our angle gauge set here, but more of a precision tool for using with the surface plate or for setting up for machining. And I've got a set here. See, it starts at about 1 degree, 2 degrees, 3, 4, 5, 10, 15, 20, 25, and 30. Those are the sets you get. And one kind of cool feature about these, as opposed to the angle gauge set, is you can add these and subtract these, similar to Joe blocks. So you can add 2 angles together to create another angle that maybe you don't have in your set, just like you do with Joe blocks. And you can even subtract angles. So in this picture on the left side, I've added the 20 and the 5 degree to create a 25 degree block. And on the right side, by basically, instead of adding them together, by flipping it over and subtracting them, I've now created a 15 degree angle using those blocks. So that's kind of cool. You can't do that with Joe blocks, can't subtract, obviously. So that gives you more combinations that you can use. But for the most part, I don't typically use these very often, other than for setting up, resting apart on a fixture maybe, but more useful for setting up on a surface plate or setting up in the machine, getting the parts ready. If you want to reach out and let me know some uses for these, I've only, compared to all the other tools I've had, I've always used those instead of these. But if you want to reach out, give me some ideas. I don't see these used very often, but they do have some uses. Instead of a sine bar, you can use these. But when you have a sine bar or a sine plate, you set up the Joe blocks and you get the angle you want as well. So we're going to wrap up our discussion. We're going to talk about angle patterns, right? That was the last, at the beginning of the video, we talked about, well, what are angles used for? And I mentioned you can use a caliper to measure angles. And in some ways that's true. It's more of a verifying that things are symmetric instead of at an angle. So when you look at a print, sometimes in this print, they've called out equal spacing of the holes at a 45-degree typical angle. And that's one way an engineer may do this print. Another way an engineer might do it is they might call a Y distance and an X distance from one of the corners for all 8 of those holes. They probably shouldn't do it that way based on the way the part appears to function, but it's up to them to decide whether they want to do it orthogonal or whether they want to do it with polar and angles. But either way, we can use our caliper to verify the distances. And so I'm going to be using the PM-03 hole pattern print. So if you don't have that one, download that. I do not have this part, but we don't really need the part itself to do the discussion. So how do we use a caliper to verify angle patterns? Well, what you end up doing, I have this part here. It has a 4-piece, it has a 4-part angle, or sorry, four hole pattern on it. So one thing you can do to verify that they're all 90 degrees, first of all, verify they're all off a center at the same angle, or same distance, my bad, my apologies. So they're all relatively the same. And then once you verify that, well, you can verify the distance between them. These are all about 509, 508. And so what I've done is I verified that the distance between each hole is the same, which means it's a square, right? Or a rhombus. It might not be 90-degree angles, but they are all equidistant. And then by verifying off a center that they're the same, I verified that it's a square. And because it's a square, squares are 90 degrees and 45 degrees, I verified this pattern is centered and symmetric, which means they're 90-degree angles and 45-degree angles on this part. So basically, whether you're called out orthogonal or radially, you can approach it the same way. I didn't really involve the print when I did that measurement with this small part here. Whether it's orthogonal or radial, I have to approach it the same way. I have to verify symmetry. So the only, I always say, check with your print first to guide your choices. And in this case, I'm looking at the print. I'm not seeing anything crazy tight tolerance. I'm not seeing true position requirements, fairly open tolerance. And this is a nice quick way to verify that the holes are put in at the correct locations. Sometimes when you're programming CNCs, some things get off. Maybe the CAD model had the hole in the wrong position and the CAM software or the 3D printing or whatever fabrication process was used, whatever production process, comes off the CAD model and then the CAD model is wrong, so the programming is wrong for the production machine. Production machine makes it wrong, and you find it with a caliper check. So I use this a lot when it's open tolerance, no true position. It's pretty much my go-to if I don't want to use a CMM, because if you check these to print, yeah, maybe you could do the orthogonal one with a height gauge and a surface plate. That would take you a while, but you could do it. To do the radial one, it's going to be pretty hard to use any tools other than a caliper to measure directly to print. So that's why I do it this way. So again, you know, there's multiple ways to call out angle patterns. Ask yourself, how do you check this to print? Do I need to check this to print? So, you know, when you're looking at it, it's a 45-degree angle, typical. That's hard to check exactly to print, but there's a substitute method that I can use with a caliper that will satisfy the intention of the print. So as I said, you have some gauges. You have a caliper, obviously, height gauge and gauge pins, bevel protractor, and CMM. They could all help with this situation here. The CMM is going to be the most accurate and easiest way to check to print, but CMMs are not always available, especially during the production process. You don't maybe want to set it up on a CMM. You want to check it while it's in production. So otherwise, if you have a CMM available, that is a better choice, but sometimes that's overkill for a lot of these clearance features or simple assembly features. So as I demonstrated with the video, one way to do it, verify off of center. Verify off of center. You can also verify the distance between the holes this way, 0.785, 0.784, and then, 0.784 this way, 0.786 that way. See, I'm getting symmetry no matter how I check it, which means this part was made probably as the way it was intended. So 513, 509, 509, 508. Let me check this one again. 509, so probably had a bad registration the first time. But, you know, you just go around and start, you know, verifying what you can. These are some different ways you can grab onto it with a caliper. If you're going to do it with a height gauge, if you look at we have a print. I have a print revision A3, which puts this in a vertical situation with a height gauge. So you can verify the centers of those holes are equal, or you can actually do the math from the surface plate to the top of a pin and subtract it, the radius of the pin. If you haven't watched the surface plate videos where I talk about how to use a height gauge and pins, go ahead and check that out. But sometimes what I'll do is just verify that, yes, each hole is at the same height, whether, you know, you don't have to do the math necessarily if they're equal. So either way, whether you do it just equal or whether you actually calculate the center of each hole, you're going to arrive to whether it's symmetric or not, and whether it's in print or not. Now, if you start measuring it, you know, checking for symmetry, and you get one that's not symmetric, then you are going to have to do the extra work to figure out the hole center. So it's faster to verify the symmetry, and if there's a problem, then start verifying the hole center to figure out what exactly is wrong. In this case, you are going to require that bottom surface there that bottom surface is actually you know, parallel to the hole pattern. If this hole pattern was put in at a slight angle to this 90-degree outside edge, it was probably different operations. That could throw you off and you wouldn't get symmetry. And the part might still be within print. You might still be satisfying this equal spacing, and 90 degrees is implied. So you might see a little bit of symmetry issue that it might still be imprint, in which case you may have to measure each hole center. So every situation is different. I can't say do it one way or the other. I just want you to know your options. And I've used this option many times. Situations just like this where I actually have a flat, lets me use a surface plate, and lets me check it very quickly. And then I want to point out you could use a bevel protractor by putting pins in the hole. And personally, I've never had a successful experience doing it this way because it can be very difficult to register the pins on this blade and on this blade. You're limited in size for the blades, and you've got to really get great registration because any little issue registering will cause a problem. So I don't recommend it. I think there's better ways that we've covered to, with a caliper or a CMM or a height gauge that are better than this situation. And like I said, I've tried it. Mathematically, it should work, whether you're measuring through the center points or you're measuring through the edges. It should be offset at the same angle, but I really haven't had much luck doing it. And I've only tried to do it in a few situations where I had no other choice. Sometimes I've worked with some large parts that I couldn't get on a surface plate, and so I couldn't do it with a caliper either, and I tried to do it with this method and I didn't have any luck, so I had to find another method to verify it. But it is a possibility. So I want to thank you guys for watching this video. I hope you learned something about the sine bars, the bevel protractors, how to use calipers to verify symmetry of hole patterns. Please check out the other video feed here for some of the more zoomed in work I did on the surface plate. And please check out my website for more training resources, more videos, drawings. And I need to thank the Laney College in Oakland, the machine technology department. They provided me this part to use in the video demo. They provided many of the tools in this series for me to use, and they're a really great program. They offer a lot of classes in machine technology, machining, manual machining, CNC machining, pump assembly and maintenance, metrology, of course, the course that I do, and CAD design. They have many classes. They have certificates available in machine technology, inspection, and others. They have apprenticeships. They can help you with your apprenticeship program if you're in an apprenticeship or you want to be one. And of course, they offer an associate's degree. And if you do any of those, if you go any of those routes, you're going to be a step up in your career for sure. So the Laney College in Oakland, community college, they offer classes year round, and great program. They have a lot there. So if you're in the Northern California Bay Area, check out Laney. And once again, thank you for watching, and I hope to see you for the next video. Thank you.